All right. So I read somewhere once that if you give students that very first question is super easy, gives them a good feeling, good confidence. So you'll see that on a few tests where the first question is pretty much a giveaway. And oh, hey, this is going to be easy. The kids do well. There's actually research that said kids do well when I do that. So I tried it a couple times. It's kind of like, limbering up before a game kind of thing. Dynamic warm-up, Connor. P positive, Connor. The letter P is used for momentum since M is used for mass. Did some of you kind of go,
yeah.
Is this a trick?
No.
No trick. True. Number 2, when you triple the velocity of an object of constant mass, you also triple the momentum. That is true. Right? Like, think about it here. P equals, this gave a few people problems, right? P equals mv. So if instead of, the mass stays the same, instead of v, I have 3v, triple it, to make it equal, right? Same thing both ways, give and take. It's going to triple the momentum, isn't it? Right? Number 3, now, can I just go through the answers here? Like I think a lot of people got 3 right. So 3 is B, vertical component. 4 is E, as in Ernie. C, this is another one of those sort of thinking ones. A car of constant mass doubles its speed, the factor by which its total momentum. In fact, would you not say that 5 and 2 are the same question, really? They are pretty much, right? Yeah. So the answer is C. When you double the speed, you also double the momentum. C. Number 6 is D as in dog. And now my pages are out of order. Number 7, the right one is D as in dog. Number 8 is A. The ball changes the momentum more slowly when you sort of, bring it in kind of thing, right? 9 is A. 10 is C. 11 is B. And there was some, I saw overall some challenges on those there. So maybe have another quite a look at those kind of questions and see if you can figure out where you went wrong. Number 12, most people got it. Linear momentum depends on both the mass and the velocity. Like there's some real super easy ones there, right? I think when you see they're almost so easy, you're not really sure what I'm trying to get at there, right? Same thing with 13. A lot of people put 0. That's not true. If the net force acting on a system of interacting objects is 0, then linear momentum is conserved, or remains the same, or is constant. Conserved, right? If the net force is 0, that doesn't mean the momentum is 0, right? If it's already moving. Number 14, why is follow-through so important for maximizing speed in sporting activities? Okay, so I wrote it out so I could scan it, which I will do and post online so you can see later as well. Following through ensures that the applied force acts over a greater time. Since F delta T is equal to M delta V, increasing the time increases the delta V, and thus the object travels faster and farther. And I know that I went through this, right? I went through it when we did the blow dart thing, right? F delta T is equal to M delta V, right? So the mass of the object remains the same. The force remains the same, but if you follow through, you increase the time. And again, that whole idea, left and right have to be balanced, right? Give and take. You increase the velocity, which makes it go farther. That's why we follow through. The opposite is number 15. Many vehicles today have crumple zones. How does this feature protect the occupants of the car? So the idea here is the crumple zone is the reverse of follow-through. It increases the time of contact, and since the mass and the delta V are the same, if the car's doing 60 kilometers an hour and it has to come to a stop, what is your delta V? It's 60, minus 60, regardless of how long it happens, right? If you're going to a stop. So again, in F delta T is equal to M delta V, you can't change the mass of the car, you can't change the delta V, and so if you increase the time, then to make the left and the right balance, what does that do to the force? Decreases the force, which is much better if you happen to be sitting in that car. That's why we have crumple zone. Interestingly enough, when cars were first built, they built them the exact opposite. They built them really strong and rigid. Bad idea. You should have listened to the scientists. Number 16. Now, for the most part, things were pretty good here. In 16, oh yes, the most common mistake, the 3.3 is west and has to be negative. That was the most common mistake. Okay, I will scan and put these up online just in the interest of saving some time. But for the most part, that was the biggest problem there in 16. 17 is the graph. The answer is minus 4.5, and you're really just finding area. There was 1 or 2 people that didn't realize they had to find below as well. Okay, but the area is minus 4.5. That was mostly good. 18 is two-dimensional.
18 out of 4.
4, yes, Mark. Okay, so the real issues with 18 were some people didn't realize it was two-dimensional. You have to find the momentums. You have to add by Pythagoras. Almost everyone divided by the mass to get the velocity. Maybe one person forgot to do that. And of course, you need the angle as well. Okay, so I'll post those. I'll scan them in and get them up right away. Okay, number 19. This is just east and west. Again, the issue was west has to be negative. A lot of people did everything good there. That's an elastic one, I think, right? Yeah. The correct answer is minus 3.19 or 3.2 meters per second. Few people didn't have the negative, I think, in the answer. Yeah. So you watch those positive and negatives, you guys. Most of the errors and the problems were tiny little boo-boos. There was a few people that had some conceptual issues. Didn't realize it was two-dimensional. Number 20, I was very pleased with. I think almost everyone got almost full. It's out of 7. I tried to circle. Some people didn't realize you added the vectors. If I have no flip or something like that, it's because you didn't reverse the vectors, right? You added them. You did this. Here's the exploding piece, right? So that one is basically it's the equilibrium, isn't it, right? So you took these two and you added them, and then you said that this was the third one, but you actually have to remember to do what? Take that and flip it. Okay, so that was sort of, I know I did that quite a bit. There was a few people that mixed up in the components, the X and the Y. I just had an arrow, put arrow backwards the wrong way. You had those the wrong way. I think that was a half mark deduction. But for the most part, I was pretty pleased with number 20. Any major questions there? I'll scan that and post it on Schoology for you. And of course, don't forget, on the exam, any questions that reappear are your chance for redo. Now, having said that, it tends to be problems that reappear. It tends not to be theory kind of questions. But I will do my best to try and find out where the major errors were and maybe try to revisit some of those theory questions. Uniform circular motion, UCM, is the next unit. We got this one and we got work and energy left. And in the old days, I used to get to some astronomy stuff. We might have time for a day or two of that. We'll see. We're actually considering that we lost that time. Although we really only lost 2 days, I think, right? With that snow, because we didn't go on. There was most of you guys were here, so we only really lost 2. So, but we're doing pretty good time-wise, I think. All right. So here's what you need to be able to do for uniform circular motion. Explain qualitatively, which means in words, why an object moving at a constant speed in a circle is accelerating toward the center of the circle. Discuss the centrifugal effects with respect to Newton's laws. Draw free body diagrams of an object moving in uniform circular motion. Experiment to determine the mathematical relationship between the period and frequency and one or more of the following: centripetal force, mass, and radius. We're going to do all 3. You may have heard of it. It's the old spinning over your head thing. Yes, you will have to wear safety glasses, and we'll start that tomorrow. It's a lot of fun. It's not the flying pig, but the flying pig is coming. That is what that contraption up there is. No, I mean, that's not true. The pig flies around the room, Mark. Whoa. Remind me to tell you the story about someone who believed that at one time. We will derive an equation for the constant speed and acceleration of an object moving in a circle. Those are the two equations right there. And that will come from the experiment we do. We're going to do the experiment. You're going to get a general sort of relationship kind of idea. And then I'll take you down a wonderful algebraic road where we derive formulas. Get the large copy that day.
Okay, can you tell us in advance what day that is before we, so that
Oh,
we get the large copy?
Sure, good point. It'll be right after we do the lab.
Because it'll be like,
It would likely be, the way things are going, it's likely going to be Monday.
okay.
Monday sized. You will solve problems for an object moving with a constant speed in a circle using those formulas. And the problem types are horizontal circles, vertical circles, and banked and unbanked curves. Like when you're going around the highway, or if you're driving NASCAR, and you know how they bank the curves? That kind of stuff.
Oh, we don't have those.
Hey?
Yeah, write those down.
Oh, you don't have those? Oh, I apologize. Okay.
On the back.
Oh, okay. All right. So this is intro stuff. I'm going to give you the answers right away. This is more, what do you already think about circular motion kind of thing? So don't worry if this doesn't turn out so good. Mark ones. Okay? I apologize for it being incredibly small, but fortunately you guys have better eyes than me. So, is it too small on the page? You can look up here. You can look up here. Did I start it? No, I didn't start it, did I? All right. So you can read that and you can make your choice, and then we'll move on here. Alrighty, let's see what we got for answers here. So number one, I got to go get my rubber stopper on straight because it's a good visual. If I can find it. Why didn't I look for it while I was sitting there waiting for you guys? There we go. I have to be careful because if I get hit in the head with the rubber stopper, we'll be all in trouble. Me mostly. You are spinning a bucket attached to a string in a circle above your head. A something force holds the stopper in a circular path. So, you know, like this kind of thing, right? Is it centripetal, or I don't know? And the answer is, oh, I got to stop. The answer is A, centripetal. In fact, both of those words mean something. Both of those words mean something, and by the end of today, you should know the difference. The right one is centripetal. In a washing machine, maybe some of you are familiar with them. I don't know. Maybe some of you don't realize there's one in your basement. In a washing machine during the spin cycle, the force is on the what, causing the water to be separated from the clothes? Is it the force is on the water, the force is on the clothes, or, again, I don't know. And the right answer? B, the force is on the clothes. The force is on the clothes, and I will explain. A tube has been placed upon the table and shaped into a three-quarter circle. A golf ball is pushed into the tube at one end at high speed. So the ball, this is sitting flat, it's on a table like this, and the ball is fired in there and it comes whistling around, and when it comes out, does it go path A, path C, or path B? What do you think? The correct answer is B. It goes flat. Goes flat, just like at the mini golf, right? Think about that, right? Right? As it's coming out there, objects in motion, stay in motion on a straight line path, right? So it's going to go straight line path. There's nothing forcing it up. Mr. Bennett is spinning a rubber stopper at a constant rate of 3 revolutions per second, like so. The rubber stopper is accelerating. True or false? True. Why is it accelerating when I stand and swing a rubber stopper in a circle above my head? See, that looks like just like me. You got the same hairstyle. Why is it accelerating?
Because the friction force.
No. Even simpler than that. Acceleration is a change in velocity, and velocity is what kind of quantity? A vector, which means it has a number and a direction. And so when I spin it above my head like that, it is the velocity's direction is changing. So because the direction is changing, it is accelerating. Is there a force?
Yeah.
If there's an acceleration, does there have to be a force? Yes. If there's an acceleration, there has to be a force. So then the question is, what direction is the force? Still spinning the rubber stopper, same picture. What direction is the force on the stopper? Is the force inwards, towards the center of the circle? Is it outwards or tangent to the circle? What did you say? And the answer is A. Oh, not one person got it. A. The answer is A. Now let's think about this. Probably that one. Let's just think about this. With a string like so, you obviously can pull on it, right? So I can pull in towards the center circle. Can you push on a string? Every year I've done that, I've never been able to push on a string. You can't push on a string.
It's sticking up and it's like
That's not a string, that's a 2x4.
like a curly little pile in front of the stopper. You
Can't push on a string. So why is the force towards the center? Well, as the stopper is moving around, right? As it's moving, I'm pulling on the string, causing it to do what? Causing it to change its direction, go in a circle. I am constantly pulling on the string in towards the center, causing it to go in a circle. Think about the moon orbiting the Earth. What causes the moon to stay in orbit? When you're driving, now this is something freaky. And every time I teach this, I go home, I drive home, and I'm forced to think about this. It's a freaky thing as you're making a turn. Okay? When you're driving your car and you make a left turn, it's friction between your tires and the road that causes the car to move to the left. And the answer to that is true. Okay? You turn your wheels, right? You turn your wheels, but for there to be a change in direction, there has to be a acceleration, and therefore there has to be a force. And so that force has to force you in the direction of the change, which means when you turn your wheels, right, your car is trying to do what? Objects in motion stay in motion. Your car is trying to go forward, and so it's actually friction that pushes you around the corner. So you think about that the next time you're driving. And if there's not enough friction, if your tires are bad or it's icy, what happens? You don't make the turn, right? You don't make the turn. It's because there's a lack of friction, a lack of force. Okay, so overall, how did we do?
I got 50%.
Overall,
I got one right.
we got 46%.
Oh.
With a standard deviation of plus or minus 1.17 or 19%. Someday remind me to talk to you about what standard deviation means.
Okay.
I'll give you the very, very quick version of standard deviation. This is a 2-day lesson in the old applied math. This is called the normal curve. Let's talk about average. I said half the population is below average and the other half is above average, right? Sort of, yeah. You want to know what marking on the curve means, Martin? I can tell you that too. This is the average, okay? X bar. So the normal curve says that 68% will fall within plus or minus 1 SD, 1 standard deviation, plus or minus 1 standard deviation. So if you've got a large standard deviation, that means that the range is, in fact, can I make this, can I do it? No, it didn't quite work. That the range is spread out. If you've got a large standard deviation, that means that you've got a lot of people way above average and a lot of people way below average, right? But if the standard deviation is small, then that means that most people are sort of clustered around that mark. That's what it means. So when you say marking on the curve, so like for example here, when we go back to here, I mean this is only 6 or 7 questions, so it's not really applicable, right? But this says a standard deviation of plus or minus 1. So the average, most people got, the average mark was 2.77, and the standard deviation, 68% of you are within 2.77 plus or minus 1.17 answers correct. Now when you talk about marking on the curve, this is how it works, right? And I don't know if they still do this at the universities or not, but everyone thinks that marking on the curve means that everyone gets a boost, and that is not true at all. Okay, let me explain. Marking on the curve means that they assume that the marks are going to be distributed normally. Okay, and it's going to have this shape when you do a plot. Okay, so what that means is the top 5%, well, they get A pluses, and the next 5%, well, they get A's, and so on. These guys get B's, and so most people get C's. Okay, now, if you mark on the curve, and I can give you a real-life example. My first year university, physics, intro physics, full year class, 2 midterms, all multiple choice, by the way. Final exam, all multiple choice. Okay. Now everyone knew that Professor, I can't remember his name, made the exam, and he made the exam from the same batch of questions that he did every year. So you went to the library and you pulled out old exams and you did them, you practiced them. And it got to the point where you could do the question, you recognized the question. You got to remember this is 1987, and there wasn't really computers, so it was all typed. Right? So the answers didn't change. So you looked at the question and went, oh yeah, I've done that one before. The answer is 6, and it's going to be C on this version. You just knew the answer. Okay? Final exam, professor, I don't remember his name, died. New professor made the exam. Guess what? Didn't use the exam bank. Made all brand new questions. What happened to the marks? How come? Because people were only memorizing, they weren't understanding, right? So the average went down. Now the average is much lower down here. No, that's a bad, I should maybe say that, right? The average is still in the middle, but the overall average is, the value, the number is lower, right? Now, I knew what I was doing. I'm not bragging, I'm Italian. I knew what I was doing, right? And so because the average went down, I actually ended up I went from a B to an A because I was in the top 10% because the average was low. Now, if the opposite had happened, if everyone had got high marks, I probably wouldn't have been in the top 10%. I would have been in the maybe top 40%. So marking on the curve can move your mark up when you are really above average. But marking on the curve can move your mark down when you are average or below. Because you got to be top to get high marks. So that's what marking on the curve is. Is that a good enough explanation? Yeah. I don't know if they do that anymore. I should ask. You will recognize the pictures because that's where I got the questions from. And I've already pre-highlighted things. So did I miss it? I'm sorry. If you whirl a tin can or a rubber stopper at the end of a string, you find that you must keep pulling on the string. You pull inward on the string to keep the can revolving over your head in a circular path. A force of some kind is required for any kind of circular motion. Any force that causes an object to follow a circular path is called a centripetal force. So centripetal force is a force that creates a circular path. Centripetal. Centripetal means center-seeking or toward the center. The force that holds the occupant safely in the rotating carnival ride, and I don't have a picture of that, is a center-directed force. Without it, the motion of the occupants would be along a straight line and they would not revolve. You've all likely been to the fair, maybe when you were younger. And they always have that one ride, right? The big white circle thing. And you walk in, and they lock you in with this dinky little chain. And does that chain do anything other than scare people? Like, well, it doesn't scare me because I get the physics. But is it there for a reason? Probably to satisfy someone that there's some sort of safety involved, but it's not doing anything. You know, the one, what do they call it? The G-force or something like that? Goes around in a circle, right? Like, it basically puts you in a big salad spinner. And you go around like this, and then what does it do? It starts to go more and more vertical, right? What's holding you in place? The chain is not holding you in place. You're not. People aren't even up against it. The chain. Inertia holds you in there. Inertia. I remember we took the kids to a place in Calgary, and they had a ride very similar, but it was kind of an old, really old ride. And we went on it, and I realized there is zero safety here at all, but it was all basically physics that was holding it together. I was like, okay, interesting.
I noticed that.
Centripetal force is not a new kind of force. It is simply the name given to any force that is directed at right angles to the path of a moving object and that tends to produce circular motion. Gravitational and electrical forces act across empty space as centripetal forces. gravitational force directed toward the center of the Earth holds the moon in an almost circular orbit about the Earth. So the Earth's gravity is a centripetal force. That's what holds the moon in orbit. Electrons that revolve around the nucleus of the atom are held by an electrical force that is directed toward the center of the nucleus. So in other words, any force that is towards the center of a circular path is centripetal. Centripetal force plays the main role in the operation of a centrifuge. A familiar example is the spinning tub in an automatic washing machine. In its spin cycle, the tub rotates at high speed, and the tub's inner wall exerts a centripetal force on the wet clothes, which are forced into the circular path. So the tub's walls push the clothes in towards the center. What do the clothes want to do? They want to go out because of inertia. Okay? The tub exerts great force on the clothes, but the holes in the tub prevent the tub from exerting the same force on the water in the clothes. The water therefore escapes. It's important to note that a force acts on the clothes, not the water, because the clothes are what goes in a circle and the water just goes to the outside and drains. Exact same principle when you wash your lettuce, right? You throw it in the salad spinner. Same idea. No force causes the water to fly out. The water will do that anyway, as it tends to move by inertia in a straight line path, which is Newton's first law, unless acted upon by a centripetal or any other force. So interestingly enough, the clothes are forced away from the water, not the other way around. When an automobile rounds a corner, the sideways friction between the tires and the road provides the centripetal force that holds the car in a curved path. If the force of friction is not great enough, the car fails to make the curve and the tires slide sideways and the car skids. And we went through that when I did the answers. Okay, so what is this centrifugal force that we speak of? Well, people say it wrong. It's kind of like, theory. Oh, it's just a theory. How that's wrong, right? Theories are explanations. They're not just guesses. Centrifugal forces, people use that word, but they don't know what they're talking about. In the preceding example, circular motion was described as caused by a center-directed force. Sometimes an outward force is attributed to circular motion. This outward force is called centrifugal force. Centrifugal meaning center fleeing or away from center. In the case of the whirling can or the rubber stopper, it's a common misconception to state that a centrifugal force pulls outward on the can. There is no force pulling outward on the rubber stopper. What force is on the rubber stopper? Centripetal, towards the center. That's what's putting it into that path. Now, if the string holding the whirling can breaks, it is commonly stated that a centrifugal force pulls the can from its circular path. So if I wheel it around my head and then I let her back and let her go at Bailey, I kind of threw it, didn't I? Just to be safe, right? What happened? There was no force causing it to go there. It was a lack of force that caused it to go there. There was no more force on the center of the string, on the string. Were you scared?
Yeah.
Momentarily?
Well, I can see on my name, I'm like, oh
Well, at least this time I mentioned, the last time I usually do it, I usually just that and I just let it go and scare people, right? But the last time I let it go and she had her head down and it just survived this much. Woo! Rubber stopper to the head.
no.
Yeah. So yeah, I yelled your name.
Thank you.
You're all good. The fact is that when the string breaks, the can goes off in a tangent straight line path because no force acts on it. Suppose you're in the passenger of a car that suddenly stops short or stops quickly. You pitch forward against the dashboard, right? You're driving along, maybe Andrew's driving, he hammers on the brakes. And Martin goes, oh, you guys are sitting the wrong way. Martin's driving, right? Martin hammers on the brakes. Andrew goes flying forward, hits his head on the dash. How come?
Didn't put a seatbelt on.
Yeah, and objects in motion stay in motion. So he keeps going. That's what the seatbelt does, is it applies a force backwards, right? When this happens, you don't say that something forced you forward. You know that you pitched forward because of the absence of a force, which a seatbelt would have provided, like Josh said. Similarly, if you're in a car that rounds a sharp corner to the left, you tend to pitch outward to the right, not because of some outward or centrifugal force, but because there is no centripetal force holding you in a circular motion as the seatbelt provides. The idea that a centrifugal force bangs you against the car door is a misconception. So let's pretend you guys are driving, we're in the Magic School Bus, it's a really wide bus, and I'm up front driving. Okay? And I flip the wheel to the left, everyone does what? Everyone goes to the right. How come? You don't go to the right, you just keep going straight. I crank the wheel, the bus goes left, you go straight. But you feel like you're going to the right. Did I say that? You feel like you're going to the right. Okay? Because of inertia. That's what's really going on. So when you swing a tin can in a circular path, there is no force pulling the can outward. Only the pull by the string acts on the can and pulls the can inward. Here's the key. The outward force is on the string. The centripetal force is on the rubber stopper, but because of inertia, what happens to tension in the string? It increases, and the outward force is actually on the string. So the idea that there is no centrifugal force is not true. But the centrifugal force with an F, the outward force is on the string. And how much is it equal to? Equal and opposite, same amount. Same amount as the centripetal. Stop recording here. Centrifugal force in a rotating reference frame. Our view of nature is very much influenced by the frame of reference from which we view it. When we sit on the seat of a fast-moving train, we have no speed at all relative to the train, but an appreciable speed relative to the reference frame of the stationary ground outside. We have just seen that in a non-rotating reference frame, the force that holds an object in circular motion is a centrifugal force. For the ladybug, the bottom of the can exerts a force. Is this the right page? This feels like I'm missing a page.
You missed the bottom.
I missed something?
You missed the one part where it's saying.
Sorry about that. Back up. I knew it felt like I missed something. Now suppose there's a ladybug inside the whirling can. So here you have the whirling can. You got a little ladybug. It's a blue one for some reason inside there. The can presses against the bug's feet and provides the centripetal force that holds in a circular path, just like the centripetal force that holds the people in the G-force. The ladybug in turn presses against the floor of the can, but neglecting gravity, the only force exerted on the ladybug is the force of the can on its feet. From our outside stationary frame of reference, so from the people, we see that there is no centrifugal force exerted on the ladybug, just as there was no centrifugal force exerted on the person who lurched against the car door. The centrifugal force effect is attributed not to any real force, but to inertia, the tendency of the moving body to follow a straight line path. Try telling that to the ladybug. So in other words, people that are outside the whirling can can't really understand, if you know I'm using air quotes, right? You can't really see, there is no force on the ladybug, but it is the ladybug's frame of reference, they feel that force. It's kind of hard to explain. Hard to understand, too. Especially when I skip steps. All right. Our view of nature is very much influenced by the frame of reference from which we view it. Now it's starting to make sense to me. When we sit on the seat of a fast-moving train, we have no speed at all relative to the train, but an appreciable speed relative to the reference frame of the stationary ground outside. We have just seen that in a non-rotating reference frame, the force that holds an object in circular motion is a centrifugal force. For the ladybug, the bottom of the can exerts a force on its feet. No other force was acting on the ladybug. But nature seen from the reference frame of the rotating system is different. In the rotating frame, in the can, in addition to the force of the can on the ladybug's feet, there is a centrifugal force that is exerted on the ladybug. Centrifugal force in a rotating reference frame is a force in its own right, as real as the pull of gravity. So depending on where you are, these forces do or do not exist. However, there's a fundamental difference. Gravitational force is an interaction between one mass and another. The gravity that we experience is our interaction with the Earth. But centrifugal force in the rotating frame is not part of an interaction. It is like gravity, but with nothing pulling. Nothing produces it. It is the result of rotation. For this reason, physicists rank it as a fictitious force and not a real force like gravity, electromagnetism, and the nuclear forces. Nevertheless, to observers who are in a rotating system, centrifugal force seems to be and is interpreted to be a very real force. Nevertheless, to observers who are in a rotating system, centrifugal force seems to be and is interpreted to be a very real force. Just as from the surface of the Earth, we find gravity ever present, so within a rotating system, centrifugal force is ever present. How many people have seen the TV series? It's on Netflix. It's called The 100. Two of you? Okay, and so the premise is there's some sort of apocalypse on Earth, and there's people living in a space station called the Ark, I believe, right? I watched a few episodes, right? And then they send the 100 of the hooligans, they send to the Earth to see if it's okay, right? So in the arc, in this giant spaceship, when they show the outside shots of it, the big thing is spinning. Why is it spinning? To create some sort of gravity, okay? And A, it's not spinning fast enough, and B, when they show the inside shots, they're just kind of walking around like regular, you know. Would that be how it is? Yeah. You would need it to be spinning fairly quickly, and in fact, people would be, there's an old movie, and I wish I could find it on YouTube. I've never been able to find it. It's a movie called 2001, Space Odyssey. Yeah, it was made in the 60s, so 2001 was like a whole long ways away. Seems funny now, right? And there's a scene where the astronaut, he's on a big rotating, kind of like a big hamster wheel, right? And the thing is spinning around like this, and it's a he. He's running, doing his exercise, and he runs up the wall and around like this. It's really cool filming for 1968, right? If you ever get a chance to see it, and I always think of that when I do this little lesson here. And that would be the type of thing that would create that false gravity in space for us, if we were to do such a thing. Okay, 2 quick questions here, and then I'll be quiet. I'll have to be quick. And I think, if I'm not mistaken, you guys have the answers at the bottom of the page, right? Don't look at them. Cover them up. Cover them up. They're upside down. Don't look at them. Don't look at them. Josh. A heavy iron ball is attached by a spring to a rotating platform as shown in the sketch, also known as a merry-go-round. 2 observers, one in the rotating frame and one on the ground at rest, observe its motion. So the one on the merry-go-round is a boy, and the one outside is a girl. Observe its motion. Which observer sees the ball being pulled outward, stretching the spring, and which sees the spring pulling the ball in a circle? So let's answer the first question. Which observer, boy on the merry-go-round or girl off the merry-go-round, sees the ball being pulled outward, stretching the spring? Connor says the first answer is B for boy. Would you agree? The boy sees the ball being pulled outward, stretching the spring? Connor's correct. Which sees the spring pulling the ball in a circle? The girl, the female, outside the rotating reference frame. Okay, so that's sort of the easy conceptual question. Here's the harder one. The spring in the sketch is observed to stretch 10 centimeters when the ball is midway between the rotational axis and the outer edge of the circular platform. In other words, they make it really complicated. Okay, so if we start like this, and we put the ball right there, and this distance is, this is midway. So the ball is exactly halfway, and then when you start to spin it, and it stretches the spring, this stretch distance is going to be 10 centimeters. Okay, now if the spring support, if the center right here, and I should have done it in a different color so I can move. If the spring support is moved so the ball is directly over the edge, so in other words, the whole post is moved out so that the ball is now right on the edge before spinning. And then you start to spin. Will it stretch 10 centimeters or more than 10 centimeters or less than 10 centimeters? If it's farther out when it starts to stretch, will it stretch more?
Yes.
Less or the same amount?
More.
And the right answer is more. You probably know from common experience, if you're on a merry-go-round, where's the safest place to be? In the center. How come? You're not going as fast. And there's something to hold on to. Right? Why are you going so fast on the outside? Because you're traveling a much greater distance, but in the same amount of time. Right? So if you're traveling faster, you're going to stretch even more and more. And that's something you'll find out tomorrow when we start whipping things above our heads.
Okay.